Good morning, everyone, and thank you very much for joining us for today's webinar, the Franklin Flats Story, Innovative Low-Carbon Strategies for Affordable Housing. My name is Felix, and I'm the webinar coordinator at the Continuing Education Department here at the OAA. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from today. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. Before we commence, I would like to share some important information to ensure an effective and professional webinar experience. Please be informed that this session is being recorded for quality and educational purposes. In order to maintain a stable internet connection, we have muted all participant microphones and disabled video feeds. We highly encourage engagement through our Q&A window. Feel free to submit any questions you may have for our speakers. These will be addressed in the designated question and answer period at the end of the presentation. Kindly note, the chat function will be deactivated following this introduction. For those seeking continuing education learning hours, please note that attendance is crucial. A minimum of 80% attendance is required for these hours to be accredited to your transcript. Please allow up to a few weeks for the processing and reporting of these hours. And lastly, please note that the presenters do not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. For accessibility, we provide automated closed captioning service available in multiple languages to accommodate the needs of our diverse audience. Now, I'm excited to introduce our speakers for today's session. Please welcome Mike Maxwell, Andrew Boosfield, Lee Scott, and Gordon Lesig. And now, let's turn it over to you.
Good afternoon, everybody. Very happy to be here to talk about a project we have up here in Waterloo Region, City of Kitchener, specifically. My name is Mike Maxwell. I'm one of the owners and principals of Maxwell Building Consultants. This is a project which, well, definitely took some time in our career, but I thought I'd start with a little bit of, is that working? Yes. There we go. A little bit of history just on the site and ourselves and how we got here. I don't know if Gordon, can you see that? Is that sharing right? Because you're the only one I can see.
Yeah, we can see the PowerPoint presentation, but it's not the presentation mode.
Apologies. If those of you who know me know this is not my strong suit. Anyway, I can get started without that, but yes, there we go. There we go. So this is the site that we collectively we picked up. I'm going to give a little bit of history about us, just so you know how we got to this sort of experiment in our career and development path. I moved to Waterloo to study business at Laurier, and we got into the student housing business because the student housing supply up here in the late 90s was quite poor, to say the least. So we started building some purpose-built student housing. Just highlighting that because at the time, urban intensification consisted of 1, 2, 3 lot assemblies. Most of the projects that were being built were stick build. There's a couple of pictures here on the slide on the left of a couple of projects we did. Each project would house anywhere from 20 to 80 students in a multi-res format. Towards the end of 2007, kind of pivoted the company to start building condos for the exact same reason that there was an underappreciation for the young people that needed housing in the student build. There was an underappreciation for the number of young professionals who were being developed locally through our universities and colleges, but also that were gravitating towards Waterloo Region to take part in the really exploding tech sector. At the time, Research in Motion was quite prominent. So we did, with many of the partners on the call today, we did a series of condominium projects, mid-rise and high-rise, a couple of projects here shown some 19 and 20 and 30-story buildings. That led us up to around 2020. Leading up to our exit from the condo market, my brother and I decided we wanted to focus exclusively on affordable housing, because there was similar to student housing and condominiums for younger people, there was a growing issue on housing affordability in general. We started learning what we could learn about affordable housing programs, initiatives, success stories from across the country, to see if we could put some muscle into the affordable housing space. So around 2017, we started doing some affordable housing, and 2020 we started doing affordable housing exclusively, leaving our former partners to continue on the condominium development. That led to this site. This is the site in question. This is the Franklin Flats project. It happened to be a 2-acre site that came to market. It was zoned and utilized as light industrial. You kind of see it in this site. This site here is improved with a 20,000 square foot single-story industrial building. It was used as, most recently, bread storage. It was an outbuilding for Dare Food, for crackers, actually, specifically, distribution center. But it also had upzoned it through a comprehensive review of zoning to mixed residential, so mixed use commercial residential. Some site stats there that it was allowed to be, had a residential FSR of 2 now as of right. So it was a good time to buy it. The zoning was already done. We just needed to complete a record of site condition and site plan. Very good central location, central Kitchener, good access by transit, not higher order transit. We have a new light rail transit system here. The closest station is probably about maybe a 10-minute walk away. So a little bit towards the edges of walkability from that point of view, but lots of bus access on both Franklin and one of the neighboring streets, Kingsway Drive. Listed for sale in 2019. We put it under contract and closed on it in March of 2020. While we had it under contract, we developed this kind of site plan. Again, just for context purposes, the goal is 4 mid-rise buildings on the 2 frontage streets with a central parking structure to provide the bulk of the parking. There's also some under-building parking under each building, and a decent size community green space or neighborhood development green space there. Centralized, as opposed to just kind of the strips that sometimes we end up developing around the buildings. So this was kind of what we were looking for as an opportunity. We had been building lots of different building construction methodologies throughout our career: conventional stick, masonry, block and core slab, cast in place, total precast, a lot of different things. But we always had this kind of itch in the back of our head that we wanted to know which was best. And of course, best is subjective, but we thought one way to do an experiment was we were going to design the same building 4 times. And the goal, we decided to keep it 6 stories to give us the most versatility in structural built forms. And that would give us an opportunity, controlling for a very short amount of time, but build the same building 4 different ways, 4 different construction methodologies. That would allow us to evaluate in not quite real time, because they weren't going to go up exactly the same time, but very close to the same time. Evaluate design efficiencies, design schedule, construction schedule, costing efficiencies, and then at the end of the day, because this is a rental project that we were going to keep, operational and energy efficiencies and whatnot with different building envelopes. We'd never had an opportunity to do that before. We'd never built the same building, or substantially the same building, the same time, because each site we purchased seemed to be a little bit different. So we would design each building custom. So this was a really good opportunity to control for a lot of the different factors. In parallel, these happen to be all affordable housing projects. So we were utilizing the relatively new National Housing Strategy from CMHC, which allowed rental projects to actually be built more cost effectively, while at the same time having affordable housing components, which is probably a discussion for another day. This is a quick summary of some of the different ideas of the structural components we were contemplating at the early stages. Some of you are probably familiar with some of them or all of them, but we were looking at using, in no particular order, conventional framing with wood eye joists, which was allowed, hybrid wood, which ends up what building A was. The first building was completed with CLT slabs and cavity wall and structural elements. We're looking at masonry and precast slabs or steel studs, full precast, total precast buildings, and then towards the tail end with buildings 3 or 4, we were looking at using some of the growing modular building technologies that are happening around Southwestern Ontario over the last couple of years. The goal was to start each building 4 to 6 months apart, which allowing for time and modest increases in inflation, we could monitor things for the most part in real time. And at the end of the day, we would know which building construction methodology was best. And the goal was to start, of course, in 2021. So if you recall from the previous slide, we closed on the property in 2020. And if many of you may remember, something else happened in 2020, which was, of course, the COVID thing. So notwithstanding what we wanted to do, we weren't really functionally allowed to control for some other macroeconomic factors that really impacted the industry. So we were hoping, like I said, to build each building relatively quickly and control for things like normal inflation and whatnot, but that went out the window. COVID had, as I'm sure many of you are aware, lots of impacts on supply chains and on inflation in general, access to trades, because all of a sudden workforces were on a regular basis cut by 10, 15, 20%. So our plan kind of went out the window shortly after starting, that we couldn't do that. And we were just happy to get the projects in the ground and completed relatively on schedule and on budget. So notwithstanding that, our first building that we built, we ended up deciding on going cavity wall and CLT. I should back up. We have a bias to that just because I grew up in a lumber yard. My parents had a lumber yard, so we grew up there. So we like lumber. So anyway, element 5, we were introduced to element 5, who's going to be talking later. We worked with them and Andrew Bousfield and ABA's team and MTE and got a CLT project design with cavity wall. Because of the logistics, we ended up being a little bit late. So we ended up taking deliveries. There's a couple of pictures there of our site where we ended up stockpiling almost all the walls and all the floor slabs on the site, because the site started a little bit late, but meanwhile, all of our walls and structure showed up. So that was fun, but luckily it was a big site. The first building, we had another 1.5 acres to lay everything down. Some challenges, I know the guys are going to talk about this a little bit later, but being a new product, CLT posed a little bit of challenges with the municipalities for approvals. Nothing insurmountable, but definitely added to some delay in approvals because it was a new product for them. They needed a little bit more information than we were expecting to provide, but we worked through that. And then, of course, there were logistical items on site due to mainly COVID. But again, we worked through those. We had a very good construction team and a really good design team. So we were able to do that. Just a couple of site pictures, and I know there'll be more of these later on as well. Some of the benefits that we ended up appreciating on building A was similar to Core Slab, but I mean, you can lay a lot of floor in a day. Our guys were able to do 7,700 square feet of slab in less than a day. We found out exactly how fast they could do it because one of our cranes blew a hydraulic line, didn't get it repaired till 11 o'clock in the morning, and they were still able to lay all the slab on the 4th floor all before they went home. So a lot of speed efficiencies. Another day for tie-ins and whatnot. And building A had a wood I-joist roof for insulation purposes. So we know that a TJ floor on the same thing took about 10 or 11 days to do. So that's a lot of savings on a 9 or 10 month build, approximately 5 weeks on the structure. Quick update on where on the rest of the project. Then we're going to turn it over to Andrew to go through a lot of the technical details, which I know is why most people are here. But building A is done, up and occupied. Everyone's in there and happy. A lot of exposed wood components, which some people ask us if we're going to paint it, but we like leaving the wood naked for aesthetic purposes. Building B started in August of 2023. We did, and this is what we're going to be doing going forward. We kind of are abandoning our idea of doing all 4 different methodologies because the data wouldn't be good. The results wouldn't really be reliable. So we're going to stick with CLT for all 4 builds and just get the design as close to perfect as we can. Luckily, some code changes allow us to change our stair columns and elevator columns to CLT. So that change was made from building A to building B. That's about a 1 week savings per floor versus our previous cast in place stair columns and elevator column. We changed our roof from wood I-joist to CLT. But other than that, that building's drywalling now. Occupancy should start early July. And building C is in for permit, I just heard, which is great because that's the same building. We're getting our design time now down to about 6 weeks on this building. just tweaks and modifications for each individual site. Tendering is now down to about 4 weeks because a lot of our trades have seen it a couple of times. We're going to start that one in July, and that one we're expecting to get the construction schedule down to 9 months through additional experience and efficiencies. Building D is probably going to start design next week. There we're making a few more changes on the suite mix just to respond to some of our partners who have said they need more 2 and 3 bedroom units. We're going to give a little bit more time on design on that one because it's not a mirror, it's a flip. But so a little bit more for that, and hopefully starting that one at the end of the year, and then just constantly analyzing and recording the schedule as well as the operational costs. So that's a bit of an overview on the project. I think Andrew is going to go next, and he's going to well, give you guys a whole lot more details.
Thanks, Mike. Just share screen here. All right, we see the rendering, do we? Good. Well, thank you, Mike. My name is Andrew Bousfield. I am the principal and senior architect at ABA Architects in Waterloo. And it's my privilege to be here to talk to you about Franklin Flats from an architect's perspective. Before I do that, certainly this project is no different than any other. There's a large team of consultants, constructors, and trades involved. Following me will be Gord Lessick from MTE Consultants, the structural engineer for Franklin Flats. And then following up will be Lee Scott from Element 5, who's going to be talking in more detail about the mass timber and CLT elements within the project. Other team key members of this project team include the constructors, Vandel, as well as planners and landscape architects from GSP Planning Group in Kitchener, our civil engineers also from MTE Consultants in Kitchener, our mechanical and electrical engineers, Collins Engineering Group and Mighton Engineering, both from Kitchener. I'd also like to just very quickly mention 4 key individuals from the ABA team who've really done and continue to do the heavy lifting. We have project architects Nadine Nandy and Dobrina Encheva, our urban design and site plan team lead Pam Toulton, and project manager Ann Sabalo. With that, I'll just quickly take us to, if the site plan comes up here. There we go. Mike has sort of shown the site plan. Now, the site plan that Mike had shown, you'll remember had a parking structure in the middle. Ultimately, what happened on site is that we were able to secure a parking reduction, a significant parking reduction from the municipal requirement of 1 car per residential unit down to 0.4 cars per residential unit. This allowed us to eliminate the parking structure and expand and extend the central amenity that you see there. The site is essentially square. It's 0.8 hectares. Each building is 6 stories in height and comprises 64 residential units. Works out to about a residential density of about 320 units per hectare. The site is serviced from the central driveway facing both Franklin along its western edge and 8th Avenue on its eastern edge. The site is generally, I would suggest, transitional, and I think Mike talked about it. There are existing residential uses to the south, but it's primarily commercial industrial on its other frontages presently. Excuse me. Garbage handling for the project is all via in-ground Moloch receptacles, and you'll see those in the center part of the site plan. Just quickly, some floor plates for you, just so you can sort of try and get an understanding of the buildings. Very simple slab type residential form, single elevator, 2 stair shafts, central corridor. You'll notice on the ground floor plan, the floor plate is narrower than the floors above. That's because the upper floors do cantilever over portions of the at-grade parking. So all of the parking now is at grade. There are commercial uses in each building which face each of the streets, so 8th Avenue and Franklin, as well as a corner lobby for each building. The upper floors, which you're looking at in beige, would be 2-bedroom units. The blue would be 1-bedroom, and the mauve or purple would be the 3-bedroom units. As Mike mentioned, the last building on the site, building D, we call it, will have a much higher proportion of 2-bedroom units. It will obviously reduce the total number of units somewhat. I'm not sure how many. I think probably about a dozen overall. So that typical floor plate would be more beige than this blue one. Building elevations, City of Kitchener, ground floor requirement, minimum height 4,500 millimeters. The other floor to floor heights here are 3,000 millimeters, excuse me. You'll recall the floor plans are very much simple rectangles. The intent was to create visual distinction between the buildings through color shifts primarily, and a kind of shall we say, an engaging sort of facade with a prominent parapet treatment, which provides each building a distinct identity, but also a kind of a continuous and identifiable skyline identity for the overall development. And you can sort of see that better in this rendering from 8th Avenue. Building A, which is the first building, is now complete, would be the building on the right of this rendering. The building B, which is currently under construction, you can't see it. It's behind building A. This would be the view to the courtyard. This would be from the south looking to the north from the neighboring residential parking lot. You'll see the central amenity space. You'll see that this is a very early rendering. There is still a parking structure in the courtyard that doesn't exist. And as well, you can see the cantilever parking condition at the buildings in this rendering. The aerial rendering, I think this is probably the third time you've seen it so far. Just to touch quickly on a couple of things, you'll notice the parking structure, which is no longer a part of the plan. The photovoltaic arrays will be installed. They're not part of the initial construction. And if you're interested why and when, Mike will probably be able to give you more detail on the photovoltaics when they'll be installed. But generally, the energy modeling is estimating 62,000 kilowatt hours per year in electrical generation for each of the building arrays once they're installed. This drone image from just a few weeks ago shows you really the state of the site as it currently exists. Building A, which is occupied, building B, which is under construction, and then building D. It's called building D in the rendering because the parking structure was C, but now building D is C and building E will be D. But anyway, the sequence really is a counterclockwise construction sequence. And Mike mentioned that C is in for permit, and we'll be starting drawings and specs on the last building next week. Another image, this time from Franklin, showing building B, at this point completely erected, the sheathing in place, roofing membranes in place, and air barrier installed, as well as the windows. This would probably be 2.5 weeks ago, maybe 3. Another image, won't spend too much time on these. This cross section through building B, and I just highlighted in green, I wanted to take you all through a couple of key assemblies, a typical roof assembly, a shaft assembly, a typical load-bearing demising wall assembly, 2 floor assemblies. There are 2 different floor conditions, as well as a typical exterior wall assembly. The roof. This is one of the things that changed, and Mike mentioned it. Building A, the first assumption or the first construction assumption we went with was TGI roof joists supporting a polyiso insulation and a mod bit membrane. I believe that was, I can't remember the actual math, but in the building B and then moving forward, we've changed out the TGIs for CLT and are able to reduce the overall roof assembly thickness by about 97 millimeters, I think. It's still a mod bit and polyiso roof on top of the CLT. A couple of images from within the building. This on the left, you see what while framing one of the upper floor suites, a corner suite in building A, you can see the TGIs at the ceiling, as opposed to this image from building B with the CLT ceiling. You'll also notice in the photo on the left, the stacked panelized walls. For building A, these walls were actually manufactured on site. An assembly line was erected in a portion of the warehouse. The walls were fabricated on site. One of the advantages, certainly when you're working with CLT, and Mike talked about the speed at which you can erect floors with CLT, if your walls can't keep up with your floors, you lose that advantage. And because we're not using CLT walls, a traditional framed wall is going to take a lot longer, and there will be delays in the sequencing. So by panelizing the walls ahead of time, we can maintain the kind of efficiencies that you get with a CLT wall with a framed wall. So a floor deck gets installed, walls are erected, bearing walls are erected, and then the suite partitions are dropped in each suite, stacked, and then the next floor comes on. So the framers are always working in somewhat contained environments, free from rain. One of the other things that we've found with the panelized wall system, now these are not really heavily automated assembly systems. They are still, or these lines are still largely human beings with nail guns assembling these walls in a controlled environment. So there's significant workplace safety advantages. As well, we've found, or we've been told by the framing contractor, that it has provided him a great opportunity for training purposes for apprentices and less experienced framers. And we know anything our projects can do to help accelerate the integration of people into trades and to continue to build skills is a good thing. This is a photo of building B just, again, a couple of weeks ago at the roof membrane. You can see the parapets and the rather dramatic geometries, as well as the support bracing, given their height. Another drone photo of building B. This is the door on the right feeds one of the exit stair shafts to access the roof. As the door on the right, or on the left, houses the hot water tanks. One of the very few gas-fired appliances in the project. Shafts. When we designed building A, probably early 2020, timber shafts were not permitted under the OBC. So cast concrete shafts were installed for stairs and elevators in the first building. Subsequent to 2022, excuse me, timber shafts were permissible under the OBC, and so we've made that shift to CLT. And in both cases, these walls, I believe, achieve. I've fallen behind in my notes. Give me a moment. I just have to. STC 62 for both walls. Excuse me. I've lost my place. I'm just going to wing it. These photos from the building A shaft in concrete on the left, you'll see the way that structural steel, some of the very little bit of structural steel in these structures is at the ground floor. And that's mainly to deal with the cantilever over the parking, as well as to provide larger open spaces for the commercial uses at the ground floor. On the photo on the right is the installation of bearing angles for stair landings within the stair shaft. A series of photos coming up about the building, showing the building B shaft. On the left, you have a typical stair shaft. You can see the angles have already been put in place to take precast concrete landings. And on the right is a good detail. One of the interesting things and the differences in the shafts is that whereas the concrete shaft is a kind of a continuous tube, and then structural elements such as floors then hang off the sides of the shaft. In the timber shaft, it is built sequentially with the floors, and you can see the floor assemblies coming through the walls of the shaft. You know, to go on site, it's really quite remarkable the accuracy with which these shafts are created and the way these panels fit together. These walls are pretty much bang on, and it's really amazing. More shots from the interior of the shaft. You can see on the left the standpipe riser, which is contained within one of the stair shafts. You'll also see that on the exterior wall, anyway, the landings do not extend to the full extent of the wall, so there is a kind of an open space out to the glazing on the exterior of the shaft. Gord will talk in more detail about the connection details, or some of these connection details. It's really quite remarkable. This plate, which really affixes the shaft at the base of the floor slab, each of those sort of lozenge-shaped elements is a screwed connection, and there's a lot of them. All of the stairs and the landings are precast concrete. The reason for this is really one of durability. The precast during construction, precast doesn't need the kind of protection, and it's got the durability to allow trades to move up and down through without needing to protect the timber stairs. Again, you can see the standpipe riser in the photo on the left. You'll notice the difference. You can sort of see on the photo on the right the difference type between the stair landing and the floor assembly, and that's really because we've got an acoustic mat and gypcrete topping that need to be added on top of the floor slab in the corridors and residential units. A couple more photos from the interior of the shafts, the timber shafts. Our typical bearing demising, so the demising wall is a 2x6 wall, insulated with 2 layers of Type-X board on one side, furring channel, and Type-X board on the other. We achieve an STC rating of 51 with this wall, and a 1.5 hour fire resistance rating. There's just a detail on the right of the way the wall and CLT come together, as well as the topping and acoustic mat. And I believe these details in this slide deck, I think all slide decks will be available to the participants to download if they wish after this presentation. Some more photos here. This is sort of more framing photos. These are both from Building A. On the left, we've talked about the wall panels stacked within the units. The photo on the right, you can start to see the topping is in place within the units. You can start to see the furring channels being installed. You'll also notice that some of the gypsum board installation has been installed at the head of the walls. This needs to be done and the fire stopping in place prior to the installation of things like the ductwork, because we need to get that fire separation integrated before we make those spaces inaccessible. So there is a sort of a sequencing thing here that has to be dealt with as it relates to managing the various trades. Some more photos. These are sort of a little bit further along. You can start to see that mechanical systems are starting to be put in place, that the bats have been installed in the wall. You can start to see the framing for the bulkheads. The bulkheads as well are pre-manufactured. The reason They are not timber framed just because they are pre-manufactured. They're lighter and easier for the trades to manipulate as they come in panels. And again, you can start to see how the fire resistance or the fire separation drywall membranes have been installed. You can see in red that the fire stopping is in place prior to the installation of the bulkheads. A typical CLT floor, not much to this. It's a 175 millimeter CLT panel with an acoustic mat and gypcrete on top of it, a 1.5 hour fire resistance rating, and an STC of 51. Some photos of the CLT from building B. You see the shafts, you can sort of see the exposed ceiling and the exposed structural steel at the ground floor in these photos. A little further along, this would be from building A. The glazing is in place, the exterior wall is in place, and the commercial space is starting to really take form. A couple more photos. We've tried to leave the CLT exposed where we can. You can, on the image on the left, you can start to see a residential unit and the exposed CLT and the exposed conduit for lighting. And on the right, again, another photo of what the commercial spaces shell condition would be like. Some photos. I know that fire stopping is never a pretty thing, but I just thought I'd throw in some of the photos showing the fire stopping. And one of the reasons that it is somewhat problematic, as much as we want to leave as much CLT exposed as possible, the fire separations at the vertical and horizontal interfaces are challenging, and just some of these things are just better left unseen. All of the units, the residential units, are heated and cooled with heat pumps and ERVs. They are ducted to the exterior, and you can start. These two images show the ceiling mounted units prior to being encapsulated within bulkheads. Just a couple of quick details here. This is the other floor condition. This is the floor condition over the cantilevered parking lot. And on the image on the left showing the insulation and hanging soffit, which is a pre-finished metal soffit. And then the image on the right showing the fire resistance rating of the steel beams, which would be within the ceiling cavity on the left. Photo of that cantilever condition prior to the installation of insulation and soffit. Typical exterior wall. Again, this is a 2x6 exterior framed wall. All of these walls that I'm talking about achieve a 45-minute fire resistance rating. There's exterior sheathing, an exterior insulation layer, airspace, and siding. Both cementitious exterior cladding and metal cladding on the exterior of the building, 2 layers of gypsum board on the interior face. I think we get fire resistance, excuse me, an R41 out of this, or 38 or 40 out of this wall, and a 1.5 hour fire resistance rating. Just a shot of the interior of the exterior wall at corner condition after the installation of the interior insulation. This is building A from summer of 2022. The structure is complete. The windows are in place at this point, as well as they are just installing some of the Romeo and Juliet or balcony sliding doors. These are pretty good shots. They do a very good job of sort of showing the components of the exterior cladding system, everything from the air barrier, the exterior insulation to the air barrier, excuse me. The horizontal and vertical furring is visible, as well as the different cladding materials. In beige would be the cement panel and the metal panel or the metal siding below it. Again, from 2002, this is building A. This says winter 2023. It's a bit confusing. This is really sort of late 2023. We probably call it winter 2024, but you can sort of see on the right building A, and on the left would be where building B was just a few months ago. So you can really see how far and how fast that structure has been erected, and then as Mike has sort of described. Lastly, I just wanted to touch on the model. I mean, Mike talked about sort of the original assumptions that the group had made about this Franklin Flats being a kind of a laboratory to test various systems to see what was most effective. And it was really because at the end of the day, affordability was the end goal. Sustainability and carbon reduction or sequestration, greenhouse gas emissions would be an outcome, not necessarily a priority. We were bringing a kind of a private sector developer mentality to the project. So ultimately, the first goal was for annual energy cost savings to be 50% of the 2015 NECB reference building. That was the goal. And we were going to explore which system would deliver the best result. At the end of the day, I think we're all very, very pleased that it was this hybrid timber approach that right out of the off the hop beat the NECB standard by 53%, and further reduces greenhouse gas emissions from 88 tons annually in the reference building to after the photovoltaics are in place down to 9 tons. The annual cost savings on a per building basis and in terms of energy costs are $42,000, and then 34,000 an additional. Well, they reduced from, excuse me, 86,000 to 46,000 or 44,000, and then after panels are in, the photovoltaics are installed, down to $34,000 per year. So that's really the exciting thing for this group, is that this project has been able to demonstrate that, you know, sustainable architecture and design is not necessarily a philosophical or moral imperative, to the extent that there is a price to be paid for that. I think what we've been able to demonstrate here is that it's just the right thing to do. It's from an economic standpoint, and that's the reason really we abandoned the experiment, if you will, and refined it to a kind of a perfection of this system. And I will, that sort of concludes my presentation. I hope I've been able to give you a bit of a flavor from an architect's perspective of the journey so far, and I will hand it over to Gordon. Thank you very much for your time.
Perfect. Thank you, Andrew. Let's get my screen up here. There we go. Hopefully everyone can see that now. Perfect. Yeah, so I'm glad glad to be here representing the sort of structural considerations that went into the Franklin Flats project. A little bit of background for me and MTE. We do quite a bit of this sort of style of construction, mid-rise with a hybrid structural approach where we're utilizing many different materials such as steel, concrete, many types of wood. We've had a few projects now. I had the pleasure of working with Element 5 with this newer CLT system that we're starting to incorporate, and yeah, it's been a pleasure so far. So I'll spend a little while just walking through some of the structural considerations we had on this one. So Franklin Flats. So this is building A. Building A is what we'd call, like I said, a hybrid structural system. So what does that mean? It basically just means that we're incorporating various structural systems and materials into one building plan and layout. trying to make use of, the advantages of each system as best as we can. So you can see here a list of what different systems were used in building A. Ground floor, like Andrew and Mike had alluded to, those were constituted from steel beams and some steel and concrete columns, largely to service the open floor plan and parking spots. Walls up above, that was light framed construction, stud walls, figure 2x6 at 16-inch conventional structure. The floors in this structure, as we discussed, are cross laminated timber, CLT. I assume most people are familiar with that at this point, but for those who aren't, it's essentially just conventional dimensional lumber laid down in sheets, and each sheet is at perpendicular orientation to the next, and they're laminated and adhered together to form a solid wood. So building A, the roof was made of wooden I-joists, and the shafts were cast-in-place concrete. So building B, very similar, except for a few changes, as Andrew had mentioned. The roof, with the comfort of the product from the first building, we moved over to the cross-laminated timber in the roof on the second building here, building B. And that was also pretty helpful with some of the support required for those tall, architecturally unique, parapets up at the roof. And as Andrew had also mentioned, that some of the code changes occurred during construction for the first building, which allowed us to move over to a cross-laminated timber combustible construction for our shafts. So hybrid structural approach. Question is why? So as I mentioned before, if we make use of several different materials and structural systems for the building, then we can make use of the advantages of each and cover sort of the drawbacks of others. When it comes to dealing with the construction of a building like this, the disadvantage of having multiple systems in one building is, we start to have a lot of cooks in the kitchen, so to speak. It becomes critical on site now to have a well-coordinated set of drawings, because otherwise, once they start putting it together and pieces don't fit, there'll be some angry phone calls and delays and things will get pushed back on site. And the other important thing to keep in mind with this is good communication with the general contractor, and hopefully a general contractor who's got a tight leash, so to speak, or keeps a tight eye on their trades to make sure everything's being well coordinated. So walking through each system that we utilized here, as Andrew had mentioned, the ground floor was largely made up of steel. The main benefit of going with steel here is to service the ideal use of the space, and that's keeping large openings. One thing on the top of the page there, where we have the cantilevered portion of the building over top of those parking spots. Very difficult to do that with something like a wood, and becomes cumbersome and timely to do with concrete. So steel just makes a lot of sense here. And then on the inside of the building, that it let us have wide open spaces by making use of that structural system. The other benefit is, if we had wood down in the ground floor, we'd have much more sheathing and shear walls throughout the floor plan that would be very hard to puncture and leave open. By moving to steel, you can see we just have the 5 braces that you can see in plan, and that lets us have a lot more flexibility in the floor plan and lets us, make much better use of that space. The other structural system used in the ground floor was concrete columns and shafts. So the exterior columns supporting the steel structure, concrete makes sense here as opposed to steel. It's more resilient, some more protection from chloride exposures out in the parking and driving areas. So that's an ideal use. And then the shafts in building A, as I mentioned, that was driven by code requirements. So having a non-combustible shaft formed from cast in place, is a requirement in the code. Cast in place we went with here as opposed to masonry, which would have also been an option. But Moving on up, so starting at the second floor, the floors were constructed, as I mentioned, from cross-laminated timber floor planks. So, you know, I think people have probably seen hollow core floor planks go in. It's not so dissimilar. They swing them into place. Though, you know, one clear immediate benefit from the wood is that it's just lighter. It's, you know, 3 to 4 times lighter than concrete is. And the benefit there is that, you know, we can swing pieces that are double spanned and much wider than hollow core would be. And as Andrew and Mike were mentioning, that allows us to, you know, swing a floor in quite quickly in as little as a day. So there's a big gain there from a perspective of construction and timelines. The other benefit is that by being able to have these bigger pieces, we can double span our slabs. So, you know, similar to a roof deck, if you have a roof deck and you can only span between 2 joists, it's much less stiff and capable than if you can have it span between 2 or 3 joists. So because of that added fixity by being continuous across the bearing lines, we can get some more stiffness and it improves our deflection characteristics of those slabs, helps keep them a bit thinner. So there are a lot of gains from a design side and from construction side in using this sort of system. Now, as you can see in the plan here, that didn't exist in all locations. So in the central corridors, we actually ended up going with a single span CLT planks, and primary reason being that if they are single spans, you can see in the bottom left corner there, we can use that double angle detail, recessed angle up into the floor space, and that lets us have a nice flush ceiling space throughout that whole corridor, which makes it a much easier time to run all of our services through. Moving on up then, once we get into the more conventional layouts and suite layouts and spacings, we can move to a more conventional bearing wall approach. These are light stud framed bearing walls. These are more conventional. As Andrew had mentioned, we can still pre-panelize these, and that helps us keep up with the rate of construction of the rest of the sort of modular system and keep the pace up on site. So moving on, so we gain the benefit of the advantages and strengths of each material. What do we pay for that benefit? And what we pay is the time, effort, and importance of coordination of transitions between those materials. So when we have multiple materials forming the structure of our building, we have to be careful in that there's no scope gaps, either between design or between construction. So detailing of the transitions between materials becomes critical. So here I'll walk through just some of our different materials and the typical transitions that we show between them. So starting off at the sort of base of the building, we you know, have various places where concrete meets steel. Now, this is not novel by any means. It's pretty typical construction detailing here. Steel bearing onto some concrete columns with bearing pads and anchor rods, and some steel columns as well bearing onto footings with anchor bolts and base plates. So pretty well understood by site, by any contractor. You know, they should be pretty on top of this coordination. And so here you can see some examples. On the left, this is the structural steel bearing onto those exterior columns, concrete columns outside of the parking spaces. And on the right is some of our interior steel beams bearing onto that non-combustible shaft in building A. So moving on, concrete to CLT. So this is a unique transition of materials that existed in building B. Building A only had CLT floors, so there was never a joint between concrete and our CLT floor generally. In building B, we had, and as Andrew had alluded to, some pretty significant connections between the wooden vertical shafts and the concrete foundations below. Now, part of the reason being, and here on the right, you can see that plate that Andrew had shown an image of. Once we removed those concrete shafts, the CLT shafts were then the primary lateral restraining system for the building. So once the building is loaded laterally with wind or seismic forces, it's transferred over to these shafts made of wood, and they have to then transfer the loads down into the foundations, both overturning, which is the connection on the right you see, and in shear, which is the connection on the left. So on the left, this is somewhat analogous to just having considering your detailing between stud walls and concrete foundations. On the left, with a stud wall, you'd have a bottom plate that you'd be anchoring into the top of a foundation wall. With CLT, we have this sort of shiplap shaped nailer plate produced by Element 5, and that is bolted in and then screwed to the panel. And then on the right, again, with a stud wall, you'd have a typical sort of Simpson hold down light gauge steel. Because we're going, bigger in scope here, we've got bigger hold downs, more load. So you have these big steel plates with, many screws. So here you can see an example of both of those connections. All right, moving on up. It's now you can see our second floor CLT landing on top of our steel framing construction. So here, again, pretty analogous to wood framing on steel. We show sort of nailer plates that get bolted on top of the steel, which then gives a material for the CLT to both land on and then be fastened into with these long screws through the top of the CLT. So this is one sort of variation. We also, I believe on the second building, actually landed the CLT directly on some of the steel and just leg bolted up through the flange, which saves a bit of material and a bit of room there. So here you can see the sort of two versions. On the right with a nailer plate and on the left with a direct connection. And then as we go up the building, so the typical floors, these are CLT floors landing onto stud framing elements. Very similar in concept, except now you're just landing on top of a double top plate instead of a nailer plate or a steel element, and making use of these very long screws, again, to come through the top of your CLT floor elements and into those framing elements. So here you can see on the left, no X-ray vision, unfortunately, but you can envision those screw heads are coming down at a diagonal through this floor, and that this joint is bearing onto a stud wall below. And on the right, this is a point of a shear wall hold down coming down through the floor. And as I mentioned in the last few details, you can see pretty serious hardware to get down through these CLT walls. That's 6-inch and 11-inch screws to come down. So everything we've looked at so far is has a decent amount of tolerance. We're not too worried about site being able to actually put it together. Now I'll give you an example of something that wasn't quite as smooth. It's this is a condition along the exterior of the building. As you can see in the top right here, it's a shear wall positioned in the second level, bearing onto steel beams in the level below. Now, we recognize this as a critical point of transition between materials and forces. The hold downs at the ends of this shear wall have to transfer their loads down to the top of the steel. So we planned for it. We made detail for every individual condition, all 5 of these. What we planned to have was an HSS tube welded to the top side of the beam with some slots in the top of it, and then ideally the hold down would land above that HSS tube, and you could bolt through to connect the hold down to the tube, which is welded to the steel beam. So the best laid plans of mice and men, as I think Mike had mentioned. It's despite all those details, considering every condition and planning for it, these tubes are welded to the beams in the plant, and the studs for those ends of the shear walls end up, in some cases, wherever they end up. and that led to this. So as you can see, not quite as ideal in this case. We have our red hold down landing at the edge of our shear wall post, several inches away from the ideal location, which would be into that HSS tube. And unfortunately, with the level of tolerance between those two, the detail had to be revised. So what was the solution? Well, ideally, if we can bolt both sides as we had planned to, that's quick and efficient and cheap to do on site. Otherwise, we accept reality and we instead decide to weld one side of that connection. So on the left, you can see the hold down plate, which has now had the bottom leg of it cut off. That side will remain bolted through to that post above. But instead, we bring it through the exterior wall, as you can see from the exterior view on the right, down to the steel beam, and we weld it to a flange, or sorry, to a gusset plate on the side of that beam. And it's a good solution, but not only a solution, it's probably a better detail to have planned from the outset. I think providing as much tolerance as possible, especially between two things with greatly different expected tolerances such as these, is good practice in a structure like this. So moving on here, the main difference, as we had discussed, between the two buildings so far, in Building A, as we had mentioned, that was a non-combustible shaft due to OBC requirements, which then in the construction of Building A had actually made some changes and now had allowed for combustible construction up to 6-story. So, we took advantage of that in the second building, and we moved over to CLT shafts. So, the reasoning here, now once we get above the foundation elements, that's one less trade on site. As you can imagine, that the time to form and pour and set up your rebar cages and everything compared to, dropping this off from the factory and putting it right in place, it's a, great savings in timing. And not only that, but the same trade who's landing your floors is now also landing all of your bearing elements and lateral elements. So it greatly reduces the amount of possibility for miscoordination between trades. Now, we still have some dissimilar material shrinkage and strain considerations between stud framing and concrete or CLT shaft framing, but so far we've had limited sort of negative experience with this differential vertical movement between the two bearing systems. The other benefit is that the CLT shafts were able to directly bear those CLT floors through the use of a continuous bearing ledger angle, as you can see in the top right there, as opposed to an additional bearing wall aligned directly beside the concrete shaft on the left. So yeah, and there you go. That's closer to the finished product of the combustible shaft construction. So with that, I will pass it along to Lee at Element 5.
Great. Thanks, Gordon. Thanks, everybody, for joining, and thanks to my previous presenters there. Did a great job summing up the building, so I will try to add to that from a manufacturer's perspective. I'm just going to share the screen here. Hopefully everybody can see that. So hopefully most of you in the audience have met me before, but my name is Lee Scott. I manage the North American sales at Element 5. Element 5 is a mass timber manufacturer. Obviously, we have our factory in St. Thomas, Ontario. There you can see a shot of the inside of the current factory. Just a little bit of a background on Element 5. We started out as a company in 2015. We didn't have the factory then. We actually started by procuring material from Europe. In 2015, the only places you could get mass timber was Europe or Northern Quebec or the West Coast. There was very limited manufacturers in North America. So the founder of the company saw the gap in the market and the potential for the huge expansion of mass timber. So I think he was on the money there, as the entire industry has exploded over the last 8 to 10 years. And in 2019, we got funding from private equity to build this current facility that we have in St. Thomas, which is 140,000 square feet. Currently, we have an annual capacity of about 50,000 cubic meters of CLT, which translates into roughly around 2 million square feet of floor plate if you're using a combination of 5 and 3 ply floor plates, and a 5,000 cubic meter capacity for glulam. So we quickly saw that we maybe undershot the glulam capacity, and as the market is exploding in North America and the demand for glulam, we've recently partnered with one of the European manufacturers named Hochschlager. You may have seen that in the news recently if you're following mass timber closely, but we got a significant investment from the Hochschlager group, and they are financing this expansion. So if I just scroll back to this photo of the current factory, you see that entire green field on the left there is now under construction for our expansion. So we're going from 140,000 square feet to just under 400,000 square feet, or roughly around 360,000 square feet. So a significant increase in footprint and capacity. Our glulam capacity will be going up about 10x, which is a great, indication for the industry, for Element 5, and just the overall level of interest in mass timber in this market. So great news there. We're super excited. We're putting a nice fancy mass timber office frontage on the building so that we stop getting all the questions about why we're in a steel factory. We will have a nice mass timber office there shortly. So that new factory will be operational by about this time next year. So right now they're pouring concrete. That photo is a couple weeks old, so they're making a lot of headway. Our main product and what we've been using on the Franklin Flats project is cross-laminated timber. And as Gordon explained, it is basically just dimensional lumber. First layer goes in one direction, next layer is perpendicular. So you end up with an odd number of layers. So it comes in 3 layers, 5 layers, 7 layers, and 9 layers. You'll see there are some different depths of the 3, 5, and 7. So each layer is basically typically a 2x material. And when that's planed down, it comes to about 35 millimeters per layer. So a standard 3-ply has 105 millimeters total depth. A standard 5-ply has 175 millimeters. Standard 7-ply 245. But if you make the middle layers thinner, you can get these optimized sections. They don't really save any cost. They will save you some building section, but to procure that thinner lumber is actually, just as costly as a regular 2x material. There's not quite the supply chain for that thinner graded 1x material. So we like to stick to the standard 3-ply, 5-ply, and 7-ply layups. And, I'll talk about how those are our most cost effective. So we do have a couple different strength grades of CLT as well. So the supply chain in Canada for softwood lumber is primarily visually graded lumber. So our most cost-effective grade is called a V2 grade. I should mention that all of the lumber that we're using is designated as SPF. So it's primarily spruce from Northern Ontario. We have a few key supply mills that we work with, but we are not tied to a specific mill. We can procure our lumber from any mill, which gives us a little bit of latitude to help optimize costs and take advantage of the peaks and valleys in the lumber procurement market. So the next grade up is an E1 grade, and that requires in the major strength direction. So if you have a 5-layer, 3 of the layers would require MSR lumber. So that's machine stressed rated lumber. That comes at a bit of a premium. So when we're trying to design these buildings, we're trying to utilize a V2 grade and optimize the building to get as much utility out of that lumber as possible. We want to keep the volume of lumber per square foot as low as possible in order to pass along the best possible costs to the project, because that is the major cost driver for us as a manufacturer. And what ends up being to these mass timber projects is the volume of wood. The major cost, probably 60 to 70% of our costs are in the lumber fiber. So it's, these buildings go up extremely fast. The installation goes up with, 5 guys in a crane. As you can see, you're putting these floor plates in extremely fast. I think we talked about Mike mentioned 7,700 square feet, but we've seen install crews do up to 15,000 square feet of floor plate in a single day. So utilizing the wide panel format that we have for the CLT just has so many benefits. If you have a 10-foot wide, which is our maximum visual panel by 40 or 50 feet long, you're putting up 400 to 500 square feet per crane peg. So you can put up 400 to 500 square feet every 15 minutes with a crane. So that's what's enabling these construction schedules to be so optimized. So our maximum panel size for visual is 10 feet wide and up to 52 feet long. A little bit about our CLT. You can see there on the left one of our panels in the factory. I just wanted to give you a close-up of just how tight those 2x6s are together. Element 5 is the only North American manufacturer that utilizes the high-end European technique of edge gluing our CLT. So as opposed to just gluing the broad face of the boards when you're cross-laminating, we actually make single layer panels, and we have a separate press that glues the short edge of the 2x6s, creates that single layer panel, and then in our CLT press, we actually cross-laminate those single layer panels. So you end up with an edge glued panel, which helps keep those lamella tight together when the building starts to climatize. Other companies, you'll see far more gaps between the boards, and that has an aesthetic disadvantage, but it also has a moisture mitigation disadvantage. If you have a rain event on site and you get water in between the gaps in the panels, you may have a schedule implication for waiting for those panels to dry out before you can pour your concrete topping. So just something that Element 5 does a little bit above and beyond some of the other manufacturers, gives us a really nice product to offer to the market. And then you can see it in action there going over the 2x6 walls on the Franklin Flats project. So Gordon did a good job of touching on the structural grid, but I really just want to reiterate how important that is for mass timber projects like Franklin and other projects that we're doing to be cost effective. I'm a huge believer that mass timber is going to be just as cost effective or more cost effective, and I think it already is, than a lot of conventional constructions. And it may end up being a hybrid construction like this. I'm a huge fan of the hybrid construction, of utilizing the right material in the right place, in the right application. But really understanding your local supply chain, understanding that Element 5 uses spruce pine fir, and our most cost-effective layups are a 175 V2 grade. And what can you get out of that for a structural capacity? So if you are 2-span continuous, and Gordon did a good job of highlighting this, you get more stiffness and strength out of that panel. So ideally, we are spanning about 6.17 meters is the maximum strength span you're usually going to get out of a 175 V2 grade on a residential project. Similar to Franklin, the Franklin grade was 6 meters, so that's one of the reasons this project is so well, because they're utilizing almost 100% of the capacity of that panel and getting as much utility out of it as possible. So the ideal panel is 3.1 meters wide, about 10 feet, by 12.3 meters long, about 40 feet. If you're 2-span continuous. If you're simply supporting, you get less strength, and you may need to increase the thickness of the panel to a 7-ply. Now, going from a 5-ply to a 7-ply means you have 2 extra layers of 2x6s. So that's going from 175 mil to 245 mil. It's a 30% increase in volume. If you have to do that throughout the entire building, you're probably just killed your performa. There are special cases like on the Franklin project where we did have to go to a 7-ply panel just because we did have a 1-span continuous or a bit of a larger bay. But for the majority of the project, we were able to utilize our most cost-effective panel, which is really why the project is part of the reason it's successful here. And then that's part of the reason we're seeing a lot of these hybrid projects successful. You really get a lot of value out of the mass timber in the CLT application. So just going back to here, when you're defining your structural grid, you want to know, is it going to be exposed? Because if you're encapsulating it, you might have a different approach. But the 175 V2 panel gets the 1-hour fire rating inherently from the panel. You're not adding any extra material for fire. It's like Gordon said, you're usually governed by deflection or vibration or some other structural characteristic. So understand if it's going to be exposed or encapsulated, understand what your acoustic concerns are, understand what your grid is, and you really need to design the architecture around the structural grid. So it's a little counterintuitive. it's hard for us when architects come to us with a floor plan and all the bays are at 6.5 meters, because that, you know, it really doesn't work for mass timber. You're going to end up with a thicker panel or a column and a beam down the middle of the unit. So this layout worked really well for the project, and hopefully that was a contributing factor for its success. For a 2-hour fire rating, I just want to quickly touch, I mean, we can achieve a 2-hour fire rating as well. So if you're in the audience and you're thinking, how do I do a 7 or an 8-story or 9-story building and leave the wood exposed, we can still use a 5-ply panel, but we may need to shorten up the grid to about 18 feet. And we may need to use that E1 higher strength CLT. Now that's probably still a better option than going to a 7-ply and adding 30% volume. It probably makes a little bit more sense to have a few more bearing lines and a higher strength CLT. So we're seeing this a lot in the United States and throughout Ontario. We're working on a 12-story building in the GTA here that's utilizing a grid similar to this and leaving the wood exposed. Now you do have to go through an alternative solution if you're going to a 2-hour exposed CLT, but those are quite easy to, you know, they're achievable for sure. So just, you know, a quick slide on designing for fire. It's, you know, it's a fairly simple calculation. Wood burns slowly and it burns predictably. I think it's 0.8 millimeters per minute. So you can quickly calculate your char depth and then understand that you have enough structural capacity left in that panel to leave it exposed for that fire rating. Andrew talked about acoustics. I just wanted to circle back on that. So achieving the STC and the IIC rating is very important for these projects. And on the Franklin project, it was actually it was actually a bit of a challenge because a lot of acoustic engineers do not want a continuous panel to span over 2 units. So they're going to try to give you mitigative measures to drywall one side of the unit or put bulkheads. We want to leave as much CLT as exposed as possible. So we actually did a lot of in-field testing while the CLT was exposed, and the CLT was performing above the design criteria or meeting the design criteria without any of that drywall added to the project. So on subsequent projects, we've been able to expose a lot of the CLT more than we could a couple of years ago. So the assembly that we're using and we've tested in the field on numerous projects now is the 175 5-ply with a 10 millimeter Genie mat by Plytech and a 2-inch concrete topping. So one of the attributes of wood is it's light, and you know, it's like Gordon said, 3 or 4 times lighter than concrete. But that allows sound to travel through it. So you have to understand your acoustic requirements, and you know, we've been working with Plytech and a couple of the other manufacturers. It's been really positive. One of the big considerations is just marrying these 3 buckets together. For us as a manufacturer, we want to make the biggest panel possible so that we get the most press utility. You want to install the biggest panel possible on site, but you have to watch out for site constraints like hydro wires or trees or tight turning radiuses. Maybe if we have to go through a back lane, we can't get a 53-foot flatbed around a corner. So you have to take all of these in consideration and actually getting the panel to site. There might be some wide load restrictions, or there might be some half weight restrictions due to the time of year. So transporting a 10-foot wide panel, it might require a wide load permit, but transporting an 11-foot wide panel might require a chase car, which might kill your whole logistics budget. So you really want to understand these 3 buckets and harmonize these together to get the most efficient panel size for the project. So just wanted to touch on a couple of the other, hybrid projects. This isn't a one-off. We're doing this all across North America. It's probably one of the most positive and where I'm seeing the most potential in the mass timber market is these hybrid constructions. So utilizing the right material in the right application. This is a project that we're installing right now in Golden, Colorado. It's 5 buildings at the Colorado School of Mines. They're all lightwood frame hybrid with CLT deck. It's going extremely well. The buildings are repeatable as well. So you're getting the advantages like on the Franklin Flats on the design times on the subsequent buildings. We reduce design time. So these are going really well. We're doing 300,000 square foot building in Washington, D.C. with this exact same scope of lightwood frame hybrid and CLT decking. And we're even seeing some, other vertical structures or material substrates to be used for that system. So cold form steel, HSS columns. the CLT is really efficient and integrates well with all of these other building approaches. So this is a 6-story building going up in Barrie later this year. We're really happy about this one, and lots more to come on that front. So I'll cut it there, and thank you for your time. And I'll pass it back to Felix.
Thank you very much for the great presentation, and I think it's time for the Q&A session. If you would like to refer to the questions that have been posted there, that would be great.
If you guys like, I can read them out. I noted that you've been doing an amazing job keeping up. We've already had 23 questions answered during the presentation from our presenters while the other ones were happening, but we still have 15 open questions. So I'll start with those. So the first one is to Gordon. Why not concrete on the podium instead of steel? I get the speed, but considering connection details, fire protections, and deflections considerations, was it more cumbersome?
I mean, purely structurally speaking, like concrete would be an option, considering it was already there in the shaft and some elements. I'd say that the connection details wouldn't necessarily be cheaper or simpler. We'd still have to have some kind of nailer plates coming down. We'd have to be careful about how we deal with like ledges that would end up forming there. I'd say the steel and wood construction, because it's already somewhat analogous to wood framing and steel beams, which isn't an uncommon system, that there's already some comfort with merging those two, more so than having big concrete frames supporting lighter CLT. So I don't know if someone else can speak to some other fire rating specific issues, but structurally speaking, either would be working.
We'll move on. So I don't see anyone else jumping in to pick up that thread. So we have a question here. Could you discuss your moisture management strategy for the CLT during construction? Did you have any issues with moisture during or after CLT assembly?
I can touch on that just to start. I mean, our moisture management plan in the factory, it starts the second that we put a 2x6, we get it from the mill. We're not sure what the moisture content is. It says kiln dried on it, but there could be some variability there. So we actually sort everything, put it in our state-of-the-art kiln, get it down to 12% moisture content, plus or minus 2%. That's what's needed in the North American certification, PRG 320 for CLT. So when it leaves our factory, it's at 12%. It probably, when it gets to site, it goes up to 15. We typically have some suggestions on moisture management on site. If the moisture content of the CLT goes above a certain threshold, say 19 or 20%, or goes below a certain threshold, say 8% or 6%, then you're going to start to take mitigative action. You typically will always get a rain event on site during construction. It's pretty hard to avoid, maybe unless you're building in Las Vegas or something, or California. But so that's going to lead to some water staining, and that's another advantage of the Element 5 wide panel format, is that you're going to have less panel joints. That's typically where that water is going to come through, and you're going to have less water staining, which translates into less remediation. But it's definitely something you want to monitor on site. And we send all of our materials bundle wrapped in a 3mm poly. And then you want to make sure that when you're having it on site, you're keeping it covered or out of in a laydown area that's dry or on dunnage, and just avoid pooling water from forming. With our edge glued panels, you can pretty much squeegee off the water as it comes, and just make sure pooling water is probably the biggest killer or causes the biggest problem. So.
Thanks, Lee. A question here from Daniel. Is there any concern and or measures taken to accommodate shrinkage of panelized dimensional lumber load-bearing walls and the CLT shaft walls?
Sounds like a good one for Gordon. The CLT is very dimensionally stable. I can just mention that the cross lamination makes it very dimensionally stable.
Yeah, I touched very briefly on that, somewhat intentionally. It's I think whether you have concrete walls or CLT walls, like Lee had mentioned, I mean, either are fairly dimensionally stable. Whereas I think what you're alluding to here is that with your top plates and your bottom plates in your stud wall construction, you'll tend to have some shrinkage and some vertical sort of deformation. So like at the outset of 6-story wood construction, I mean, we're all pretty concerned about some of those differential vertical movements. So far, our experience in building these has been that hasn't really come to pass in the way that we expected. So it hasn't seemed to be, come to fruition as much. And it kind of depends on your layout as well. Like you can handle some differential vertical movement if you're not dealing with, doorways and things like that, crossing between the threshold of those two materials. And the layout here, I think, led itself to not have that issue quite as much. So on this specific project, it wasn't as much a concern.
Let's see. We had some really nice comments, so I'm sorting between a whole whack of thank yous and positive comments and kudos. So here's one. Andrew, could you summarize the choice of wood frame infill walls instead of steel studs?
Yeah, I mean, there's really no real magic to it. It really had to do with the fact that we had and continue to have production lines building the walls. So we're able to build all walls in one facility. Once we have the framers on site, they can just roll. And that was really construction sequencing, I think, was the priority there.
Yeah, I'll just add to that. I think some of the magic of these hybrid buildings is having an installer that can do both. Because as you saw, the speed of the CLT going in, you don't want to have a separate crew putting up all your walls for a week and then have the CLT crew come in and put on the floor one day, mobilize, demobilize, and come back and forth every couple of weeks. So you have to have the same person. So we had contract framing who did an amazing job on both the walls and the floor. So that's kind of the catch to these hybrid constructions, as it makes sense from a construction sequencing perspective to have the same crew putting up everything.
Well, one exception and one small change we did make from building A to building B, to echo Lee's point of, you want to minimize the number of handoffs you have from one trade to the next, and then, passing the ball back. One exception, one change we did make on building B to C is the wet walls we changed to steel. Because of course, the framers go up, they're done the building, all the interior walls are done. The plumbers are going up, and then we're doing a wet wall in front of it. We don't want to bring the carpenters back to frame, a 10-foot wall in every apartment or a 5-foot wall in the bathroom. So we did switch those to steel stud, because by then the drywallers were already on site. Steel stud guys were already on site doing the odd shaft wall and fire separations. So getting them to do a steel stud wall, not that the carpenters couldn't have, but by then they've already moved on to the next project. They're working on these projects somewhere down the road. So that was one change we did, but that was the only one that we're asking the steel guys to do.
Thank you. How do you ventilate the apartments without cross-contamination? Any takers?
I would ask for more clarification. I'm not talking. Are they talking about makeup air? I'm not exactly sure what
Yeah, it's a very short question. So,
Yeah.
William, if you're still on with us, maybe type in the question again, and we can maybe get to it at the bottom if everybody's still online. So, I'll give you William another chance to put that question in with a bit more detail. Next question: could you discuss any major hurdles with CMHC related to energy requirements?
We're going to need another session. Yeah. Basically, CMHC is great with their financing in that they offer high ratio, low interest loans, but there's a whole series of extra hurdles to do. Energy modeling being one of them. You heard Andrew allude to. We need to be minimum 50% better than the National Building Code. In terms of are they auditing / reviewing those performance models? I don't think we got any feedback from that. We did the energy modeling, and it was kind of pass fail. With respect to that, other CMHC issues, I mean, geez, Michael, we can talk about that for hours, but sure.
Another question from Michael. In terms of sound, how does the assembly fare in terms of impact noise and chair drags?
Well, I guess what we can say, I had answered this question, I think, a little earlier, just in typing our similar one. At STC 51, I would agree that the floor assembly in and of itself meets the criteria. As of yet, so building A has been occupied for several months. We have received no commentary or negative commentary anyway with respect to the performance of the floor assembly. So at this point, I guess my answer would be yes. It seems to be standing up to people standing and walking. You know, I think there is time. I mean, if we needed to change and upgrade the assembly, you know, we could on buildings C and D, but at this point, it doesn't look like that's going to be an issue.
Yeah, the CLT itself gets an STC of about 41 for a 5-ply, so you need that extra matting. And I know Plytech makes that in all different thicknesses too. And they have a great design guide online that shows all of the different STC and IIC ratings that you can achieve with different assemblies. So
this is an easy one. Are there laundry machines in the suites, or is there a common laundry room?
Easy. Oh, let me take that one, Andrew. It's easy. There's a common laundry, common coin-op laundry on the second floor. Yeah, just not every in-suite.
Next one for Lee. What's the current practical height limit for CLT construction in Ontario, considering cost, structural design, authorities, and permits?
yeah, so I believe currently you can go up to 12 stories. There was just an announcement that they're going to be changing that to 18 stories, which is great news. The threshold to go from 1 hour to 2 hour fire ratings is typically at about 6 stories. So 6 stories and below, you can typically expose most of the mass timber, which is great. It saves you, money and time on drywall, and allows you to appreciate the aesthetic of the timber. Once you go typically above 6 stories, you go to a 2 hour fire rating, and you're going to change your structural approach to either encapsulate the mass timber or expose it and have the timber meet the fire rating and go through that alternative solution. We are looking at buildings that are above 12 stories right now throughout Ontario and the United States that are beyond the code. So there's always the opportunity to go through an alternative solution. We just recommend, getting a great engineer of record. Gordon's probably available, and and bringing on manufacturers as design assist partner to work through those constraints.
We had another question here about costing, but that was asked and answered a couple of times. So if you just go to the answers that are typed within the system, you can absolutely pick out that one there. So I'll jump to the next one. I'm curious about the floor assembly shown in the 50 millimeter CLT topping on the rubber acoustic mat. Is there any concern about the concrete cracking when interior partitions bear on the topping with the acoustic mat underneath? Are there any strength characteristics of the acoustic underlay that you need to bear in mind? Detailed. So the first one is concerned about cracking.
Yeah. No concerns yet, I guess would be the answer. We have not experienced any of the issues that this question raises. And so to that extent, the detail has not changed. I guess that's, right now, that's the best I can come up with. We're not seeing kind of deflection or stress on the topping under those wall conditions that are described. And of course, remembering that any of the bearing conditions bear directly on CLT, not through the topping and the acoustic mat.
Yeah, and just to add to that, Andrew, we see the 2 inches as pretty much the industry standard throughout North America. And on a lot of these projects, or another way to approach the mechanical, electrical, or at least the electrical conduit, is to run that conduit through the topping on the top side of the panel, and then coordinate where your junction boxes and lighting are, and drill out those penetrations in the factory and have that conduit come down through. So they're even doing that with a 2-inch topping and having that conduit run through it and still not experiencing cracking. So I think here, where it's just a solid topping, we would, I'd be surprised if there was, but it's pretty standard across North American design.
Fantastic. And so there's one remaining orphan question, but you're not going to be able to answer it because it just says, what are the cost implications? But there's no detail about cost implications of what. So we will thank that person for their interest, but we'll not move on that one. So that's it, you guys. So asked and answered 42 questions all together during this session. So I think that's a real tribute to the topic and the great job that you guys did presenting today. So thank you. And then I will back off and hand things back over to Felix.
Thanks, Sarah.
That's great. Thanks to our panelists for a great webinar and discussion today. Thank you also to everyone who attended. And as we conclude this webinar, I would like to draw your attention to some announcements. The next webinar takes place next week on May the 2nd, also at 11 a.m. and the title, ISO 19650 for Architectural Companies. As mentioned, the OAA will report your participation in this webinar to your transcript. Therefore, there is no need for individual reporting on your part. We kindly ask for your patience as we process and confirm the accreditation of the hours within the next few weeks. Additionally, all attendees will soon receive the presentation file via email along with a link to provide your feedback. Once again, thank you very much for your attendance and have a productive and pleasant remainder of your day. Bye-bye, everyone.
Thank you.